All right, so this is part 8 and last part of this chapter, entropy. We can actually continue this forever, doing more and more problems, but I think we have done enough, and we're going to do several more problems in this chapter to prepare you for the exams. Okay, so this is problem 104. 7104, steam enters an adiabatic turbine. So pretty much, in all of these problems we have, if you have noticed, we have assumed that the turbines are adiabatic, but not necessarily reversible. So at 8 megapascal and 500 degrees C, this is superheated steam with a mass flow rate of given and leaves at 30 kilopascal here. The isentropic efficiency of the turbine is 90%, so this turbine is not reversible, it is irreversible. Isentropic efficiency is given. Neglecting kinetic energy, change of the steam, and of course the potential energy, determine the temperature at the turbine exit and the power output of the turbine. Okay. Temperature at the exit and the power. So this is our turbine again. Oops. And the inlet condition, we go ahead and use table A6. So table A6, we need to mention that, as I have said it multiple times. Please write down all of the details. So P1, 8 and 500, you can go use the superheated table, read H1 and also read S1. So we're gonna need entropy in order to find the other properties at the exit, because at the exit only, as you see, the pressure is given, nothing else is given. So you would need a second property. That second property for the steam at the exit, this is the saturated, so you're gonna use table A5 for the turbine exit. The pressure is given, and as the second property that you need, you just say that S2 is equal to S1. But you say S2S because even though the turbine is irreversible and non-isentropic, first you assume that it is isentropic, and then go ahead and take into account the isentropic efficiency. Without this, you will not be able to do the problem. So S2S is equal to S1, and if you go to the saturated table, then first you need to find X2S, the quality under this condition, the quality of the mixture, and the quality based on the knowledge of the entropy, because you know the full amount of entropy based on entropy constant condition. You can use this S2S, which is equal to S1 from here, and then SF and SFG at 30 kilopascals. So you find quality equal to this value. Now that the quality is known, you can go ahead and find enthalpy equal to HF plus X HFG. And you find the enthalpy based on the isentropic assumption. So if you, let me show it. So let me show it on a TS diagram for you to understand what's happening. So TS, and this is our dome. This is a little bit too wide. So let's say this is state 1. This is turbine inlet, superheated. And then if we can assume constant entropy, this would be the line. This would be line. This point would be point 2S. Oops. So this is based on isentropic assumption or based on constant entropy assumption, and then in reality point 2 will be probably somewhere like either here, either superheated or probably here. So this would be point 2s and this would be actual point 2. So this would be actual point 2 and this would be point 2s. Okay, so now we have for point 2s we do have the enthalpy. So here we can use the definition of the isentropic efficiency of the turbine, which is equal to the isentropic work in the denominator, and in the numerator the actual work. So actual work is H1 minus H2A, and isentropic work is H1 minus H2S. A means actual, S means isentropic. So based on this you can find H2A, which is the enthalpy of this actual point 2. So let me call this point 2A. Alright, so therefore H2A can be found based on this equation. So now that you have the pressure 2A, which is still 30 kilopascal, the same as 2S, and you have H2A, you can go ahead and find temperature 2A. So the thing is that it's possible that point 2A remains under the dome, or it may actually become superheated a little bit. So 2A may be, depending on how isentropic the process is, it could become superheated, but in this case it appears that it is actually still under the dome. So therefore T2A is the saturation temperature associated with 30 kilopascal, which is 69 degrees C. And to verify that actually point 2A is under the dome, we need to look at the table and show that, okay, this H2A, if you look at for this condition for saturated, so it means that your H2A is less than Hg. So you need to write this down as well. This proves that actually you are under the dome, it's not superheated. However, if H2A is greater than Hg for 30 kilopascals, then it means that you will need to go and check the superheated table. So, all right, so part B, in part B, we need to find the turbine work. So m dot 1 is equal to m dot 2 equal to m dot. This turbine just has one stream coming in, going out. If we write the first law, a steady flow process, E dot in equal to E dot out. Energy in is m dot h1, energy out is turbine work, and m dot h2. And it's based on adiabatic turbine, kinetic energy, potential energy 0. You must write all of these assumptions. So I've seen that some people just write that m dot out is equal to some people just write that w dot out is equal to m dot h1 minus h2. This is correct and incorrect. It's incorrect because it's based on many assumptions, and it really doesn't show whether you know what's going on during this process or not. So please make sure you write all of the details. So in order to find the turbine work, we do have everything. We have m dot given, we have h1, and we have h2. So in addition to this, we could have written this as in another way. So this is also equal to the isentropic efficiency of the turbine multiplied by H1 minus H2S. So that would be another way of finding the turbine work. directly using H2S. So this H2 that you see here is H2A, and this H1 is just H1, H2 is H2A, the actual enthalpy at the outlet. Okay, so let's do 7198. So air enters the evaporator section of a window air conditioner. So this is like an air conditioner. There, it has a coil. In the coil, you have refrigerant R134A. The inlet condition is given. So, and the outlet condition is given. Saturated vapor for the air, its atmospheric pressure 100 kilopascal. It comes in at 27 degrees C. And the volume flow rate of the air is given. The refrigerant enters at 120 with a quality of 30% at the rate of given m dot, and leaves as saturated vapor. So here x is equal to 1 at the same pressure. Determine the exit temperature of the air. So we want to find the exit temperature of the air, T here, and the rate of entropy generation for this process, assuming A, the outer surface of the air conditioner are insulated, so under insulation condition, and B, under the assumption that heat is transferred to the evaporator of the air conditioner from the surrounding medium at 32 degrees C at the rate of 30 kilojoules per minute. So we want to find the final temperature, the outlet temperature of the air, which is given to the room, and the entropy generation for this process under two assumptions. Assumption one is that the process is, assumption A is that the air conditioner is insulated. Assumption B is that some heat is actually given to the air conditioner, for instance, solar irradiation, something like that. Okay, so let's name this for the refrigerant, we call it 0.1 and 0.2 in inlet and outlet, and for air the inlet is 0.3 and the outlet is 0.4. So for air, the problem doesn't state what to do exactly, so we can go ahead and use constant specific volume, so based on the approximate solution. For refrigerant, we go ahead and use the refrigerant table. So for refrigerant, P1 is given, X1 is given from the refrigerant table. So what table was it? So here it says the table A11 to A13, but you actually must tell what table. So this is saturation, so I believe this is based on table A12, the pressure table. So you need H1, so you find H1 equal to HF plus XFG. And you need to find the entropy generation, so you need to find S1 as well, because you need it for entropy. S1 is also SF plus SFG. The exit of the refrigerant, the temperature is given, and it says that it's saturated vapor, so X2 is equal to 1. So it means that H2 is equal to Hg, and S2 is equal to Hg. S2 is equal to Sg, so this is a typo. So this S2 is equal to Sg. So from the saturated, from the two-phase table A12. Okay. So for air, we go ahead and read R from table A1. So R comes from table A1. We need to write it down. We do need the mass of the air. The volume flow rate of the air is given, but the mass flow rate is not given. So we can use the ideal gas law to find the mass. We do need the mass in order to find the entropy change, and also yeah, probably it's only needed for the entropy change. So PV equal to MRT, we can actually have it PV dot equal to M dot RT. So in the rate form is also valid. So pressure of the air is given, its volume flow rate is given, and this volume flow rate is in per minute. The mass flow rate is also obtained per minute. We need to be careful. If it's needed, it has to be converted to per second. Okay. So the problem asks us to find the outlet temperature of the air, T4. So in order to find T4, we need to write the first law for the entire system. So we need to see what energy is coming in, what energy is going out. If we consider this as our entire system. So let's see what energy is coming in from 3 energies coming in, from 1 is coming in, and then from 2 and 4 energy is going out. And there's no work. So heat can be in part A of the problem. Heat transfer was neglected. And in part B, heat was actually added to the system. So we need to do it based on 2 assumptions. So first, let's write the first law and find the outlet temperature of the air, and then calculate the entropy generated during this process. So for this process, we will see that we need Cp. For Cp, we can use Cp at room temperature, for instance, or ideally we need to find Cp at the average of T3 and T4. But because T4 is not known yet, we can use Cp for the room temperature. So because it's an approximate solution and T3 and T4 do not change much, so it will not affect the problem. So we can use Cp at room temperature, but we need to write it down. Okay, so considering that system which contains the evaporator and also the air section, all of it. So mass in is equal to mass out. It's a steady flow process. Therefore, it means that the mass of the air which is coming in is equal to the mass of the air which is going out. And then for the evaporator, there is also just one stream of evaporator. So we call them m dot air and m dot r the refrigerant. So the first law for the entire system, everything together that I drew in the previous slide, E dot in equal to E dot out. So what is coming in? Energy, one stream of refrigerant is coming in, the stream of air is coming in. What's going out? One stream of refrigerant going out, one stream of air is going out. For part A, heat transfer is 0, work, there is no work in either case. Kinetic and potential energies are 0, that this has to be written down. So if we go ahead and instead of m.1 and m.4, we write m.r from here. Instead of m.1 and 2, we write m.air. Then we will have this equation m dot refrigerant H2 minus H1 which were found, and for air, H3 minus H4, by approximation, we can write it as Cp T3 minus T4. And we know that T4 is unknown. If we rearrange this equation, we can show T4 as a function of other variables. Everything is known. We can plug in and find T4, the temperature at the exit of this evaporator. The temperature of the air at the exit, which is quite low, and I don't know why someone would need a temperature of minus 15. And the reason is that the inlet temperature was like 27. It's like if you turn your air conditioner in the winter, or you turn it on when it's not needed. So, but don't worry about the fact that this number is too low. It's not, probably doesn't show an actual situation, or maybe this is an air condition, this is a system, this is a refrigeration system, for instance, rather than a window air conditioner. Also, we need to consider the fact that we assume that there is no heat from the surrounding. If we consider the heat coming to the air conditioner from the surrounding, the problem would change, and that would be another part of the problem that we will do. Okay, so that was the first law. How about the second law, the entropy balance? So the second law, or entropy balance, says that entropy in minus S dot out plus S generation is equal to the change of the entropy of the system. Because it's a steady state process, the entropy of the system doesn't change. So entropy in is because of the air stream bringing in entropy, refrigerant brings in entropy. Actually, M.1, I believe, was refrigerant. So refrigerant brings in entropy, air brings in entropy. They also take out entropy, both refrigerant and the air. So this is entropy in and entropy out plus entropy generation equal to 0. So we want to find this entropy generation during this process, which is an actual process. It's not reversible. So therefore, for the refrigerant is M.R S2 minus S1. We actually found S1 and S2 from the tables. For air, it's an ideal gas. We need to use a different approach. For an ideal gas, we need to use the approximate relation given in the lectures. So Cp, a natural log of T4 over T3 minus R natural log of P4 over P3. So these were given in the lectures. So for this process, for the air, we assume that the pressure doesn't change. So this term is 0, however, the temperature changes. So T4 over T3, we already have T4. So we plug in the numbers, make sure that the numbers are in Kelvin, not in centigrade. Whenever you have a ratio of the temperatures should be absolute temperatures. But if they are temperature difference, it doesn't matter whether they are in Kelvin or in Celsius. So we find S4 minus S3 and then plug in the numbers up here and find entropy generation. So this was based on the assumption that Q is equal to 0. Now part B of the problem is the same thing, but we do consider some heat addition to this control volume. So if you repeat the process with a non-zero Q, everything is the same as before, except that this Q is now non-zero. So we will have this Q term. If we repeat it, the temperature will be higher than before, but still it's negative. And if we write the entropy transfer as well, the entropy balance as well, entropy in minus entropy out. So for the case of entropy in, This time entropy in is not only because of the refrigerant and because of the air. Some entropy is also coming in because of the heat transfer. So the heat transfer was given and the temperature of the surrounding was also given. So this is the basis for finding this entropy, which is coming in because of heat transfer. Q in over T surrounding. So if we rearrange, so everything is the same as before, except that this time T4 is different from the previous temperature. For refrigerant, everything is the same, I believe, but for the air, we need to recalculate entropy difference, entropy change of the air with this new temperature. So for refrigerant, the same as before. For the air, only T4 is different this time, everything else is the same. So entropy generation at this time is larger than or greater than the entropy generation in the previous case, because this case involves heat transfer as well. So since heat is transferred to the system, it brings in entropy as well, or generates entropy. This is problem 200, 7200. Consider a well-insulated horizontal rigid cylinder that is divided into two compartments by a piston that is free to move, but does not allow either gas to leak into the other side. So the piston can freely move. What does it mean? It means that the pressure, because this piston can easily move, freely move, if the pressure increases in one side, then it will pushes the piston to the other side. So eventually, because of this piston, the pressure remains the same on both sides. Initially, one side of the piston contains what you see here, the amount of nitrogen, the other one hydrogen at given same pressure, different temperatures. Now, with these initial conditions, now thermal equilibrium is established in the cylinder as a result of heat transfer through the piston. So heat transfers from nitrogen to helium using constant specific heats at room temperature. So this is a simplification. So it means that you use CPCVs when whichever which is needed at room temperatures from table A1 or maybe A2, determine the final temperature, final equilibrium temperature in the cylinder and the entropy generation during this process. The problem has another part. What would your answer be if the piston were not free to move? Okay, so the assumptions are that we consider the two gases as an ideal gas with constant specific heats. And we do not consider the effect of the container itself in terms of energy storage, because if, for instance, the piston is massive, it may store some of the heat and does not give it to the other gas. So this is a very interesting and important assumption. The cylinder is well insulated and heat transfer to the surrounding is negligible. So, okay. So first we need to, understand the problem and see what has to be done. In the first part, we do need to find the final temperature. And you may want to start from this equation in order to find the final temperature. The first law, energy in minus energy out is equal to the change of the energy of the system. Okay, energy in, if you consider both of these two together, the cylinder, the two gases together, there is no energy in, there is no energy out. So on the left side, you do have 0. Changing the energy of the system, therefore, is delta U, neglecting kinetic and potential energy, is 0 for both gases. However, one gas gives away heat, nitrogen gives heat to helium. So that has to be considered. So therefore, delta U equal to 0 is equal to delta U of nitrogen, which is non-zero, plus delta U of helium, which is non-zero. So 0 is equal to delta U of nitrogen, mCv delta T of nitrogen, plus mCv delta T of helium. So T1s are known for both gases. T2, which is going to be equal for both gases, is unknown. So if we plug in the numbers for, okay, so now, all right, so now you do need the mass of nitrogen and you do need the mass of helium. How to find them? From the ideal gas law. Mass of nitrogen and mass of helium in each compartment. PV equal to mRT. The pressure for the initial condition, the pressure is known, 500 for both of them, the same pressure. Volume is known, temperature is known. Need to convert the temperature to Kelvin. So we can go ahead and find mass of each of these gases. Then we plug in the masses in the first law in the following, this equation here, and if we rearrange, we can find the final temperature, which is 52.7 degrees C. This is the temperature of the cylinder, temperature of helium and nitrogen, both is the same temperature. So now this was for the case where the pressure remained constant, where the piston freely moved. So the question is that if, for instance, we wouldn't let the piston to freely move, keep it fixed in place, would the answer change? So for this process, did we actually use that assumption that the piston can freely move? It appears that we never used that assumption. So the answer would be the same if the piston were not free to move, since it would not affect, the process. We didn't use pressure. So here we only use CV. There was no pressure effect in this part of the problem. Part B, we want to find the entropy generated during this process. So we write the entropy balance. This is the same for every problem. Entropy in minus entropy out plus entropy generation is equal to delta S of the system. If we do have a steady flow process, this becomes a dot. We put a dot on top of them. So entropy in, entropy out, there's no inlet, there's no outlet, there is no heat transfer. So entropy in and entropy out is 0. Then we always have the entropy generation term, and then it's equal to delta S of the system. So delta S of the system is delta S of nitrogen plus delta S of helium. Okay, so how to find delta S of nitrogen and delta S of helium? So we need to think a little bit about this. So we need to go back to our, let's say, lecture notes and see that the entropy change of a gas, of an ideal gas, can be obtained from this equation. For instance, the ratio of the temperatures and the ratio of the pressures, or the ratio of temperatures and ratio of specific volumes. And we do need the mass that we do have. And we already do have the temperature T2, and we had temperature T1 for each gas. But how about the pressure P2? So in the case of the piston freely moving, let's focus on that. Piston is freely moving. So what is P2? P1 is known, but P2 is not known. So we need to find P2. In order to find P2, it's like we assume that, for instance, something like there's no piston at all. So we can go ahead and write the ideal gas law for both gases. So for this purpose, you could do two different approaches. One is that you write the ideal gas law for each of these two gases for condition 2, for the final for state 2. So meaning that you write P2V2 equal to mRT for each gas, and then in this equation you wouldn't know the volume. Volume would be unknown, final volume, and also the pressure would be unknown as well. So you have like two unknowns here for each gas. So when you write the ideal gas law for one gas, both the pressure and volume would be unknown because the piston has moved. You don't know how much it has moved to the left or right. But when you write it for both gases, then you see that the pressure is the same in both of them. And you know that the sum of both volumes, the sum of V1 plus V2, would be equal to a fixed amount of 1 cubic meter plus 1 cubic meter equal to 2. So this would be one approach, the approach that I thought about. There is also another approach of the book which is interesting. So for this purpose we find the number of moles for nitrogen and for hydrogen, and if you for the number of moles is the mass divided by the molar mass of each gas. So therefore we can find the moles of each of these two gases, and then we find the total moles that we do have available there. Then another form of ideal gas law is that PV, total volume, is equal to N RU, the universal gas constant, times T. So in this way of writing the ideal gas law, R is actually the universal gas constant. So it's both the same, it's the same for both gases. And we already have found the total number of moles in the system. So with this, if you plug in the numbers, you can find P2, the final pressure after moving from state 1 to state 2. So this is the pressure in both gases. Now you can go ahead and find delta S of nitrogen and delta S of helium using the ideal gas law entropy change. Everything is known, so entropy of nitrogen is found. Similarly, entropy of helium is found. So similarly, this would be the entropy of helium, entropy change of helium when it moves from state 1 to state 2. And then the entropy generation would be the sum of these two entropy changes. So as you see, one of them gains entropy, the other one loses. The one which loses heat, nitrogen is losing heat, so its entropy decreases. Helium is gaining heat, its entropy increases, so the sum of these two must be positive because entropy generation is always positive. Now the question is that if the piston were not free to move, then what would be the answer? So the answer would be that still the temperature would be the same, T2 would be the same, and then in this case the volume of each gas would not change actually. So this case is actually easier to do. In this case, we go ahead with the entropy change based on the volume change. Instead of pressure change, we go with the volume change, and we see that, oh, these terms do not change. Nice. So entropy change of nitrogen system and helium system would be easily found. Again, you see that in this case, the nitrogen is again losing heat, therefore its entropy decreases. Helium is gaining heat, its entropy increases. The sum of these two entropy generation would be again positive. So this was a kind of advanced problem for the concept of entropy generation in an ideal gas. So one last problem here, we do have an insulated rigid tank which contains air at given temperature and pressure with given volume. A valve connected to the tank is now open and air is allowed to escape until the pressure inside drops to 200 kilopascals. Okay, so we open the valve, the air escapes, the pressure drops to 200. The air temperature during this process is maintained constant by an electric resistance heater, so it performs work. Work is converted to heat, so the temperature doesn't change. We want to determine the electrical energy supplied during this process, so we need the first law, and we need the total entropy change. We need the second law and entropy balance. Okay, and this is not a steady flow process. This is like a uniform flow process that we had in chapter 5 when we studied the first law. So we considered two special cases. One was a steady flow, one was uniform flow. Because in this case, when you open the valve, you can assume that the air which escapes at a like constant on average properties from this valve. Okay, so the problem didn't mention to use a specific heat, constant specific heat or approximation. Therefore, we're going to use table A17, and this is air, table A17, in order to find exact solution. So some assumptions listed here. It's an unsteady process. However, we can assume that it's a uniform flow process. Kinetic and potential energies are negligible. We need to write them down. And the tank is insulated. There is no heat transfer. And air is ideal gas. And we're going to use exact solution, variable specific heats. If the problem tells you to use constant specific heats, then you can use like delta H equal to, or delta U equal to C delta T. Otherwise, you would need to use the A17 table, which is the exact properties table. So to avoid ambiguity, I usually tell whether you should use a specific heat or you should use table. So this is exact solution. It means that you should use table. So, all right, so the initial temperature is 330, the final temperature is 330, and also the temperature of the air that exits the tank is 330. So it's same temperature. So enthalpy for all cases, enthalpy is found from the table, and we also need internal energy because it's a uniform flow process. Later you will see that internal energy is also needed. So we read this from the table directly. There's no need for interpolation or anything. Then if you write the energy balance for this uniform flow problem, mass in minus mass out is equal to the change of the mass of the system. There is no mass in, we just have mass out. So the mass out, we can show it here as ME, mass exit. The mass which leaves the tank is equal to initial mass minus the final mass. So now we can go ahead and, using the ideal gas law, find these masses. M1 is P1V, which is constant, RT1. And M2, the pressure, the problem tells us that pressure 1 is 500 and the final pressure is 200. So we can find M1 and M2, and therefore we can find the mass that has left the tank, M equal to M1 minus M2. So that's the mass balance. How about the energy balance? A uniform flow process, energy in minus energy out is equal to delta E equal to delta U, because kinetic potential energies are zero. Energy in, if you look at your tank, there is no heat transfer, you need to write it down, Q is 0. So heat transfer is 0, but you do have work transfer coming in. So this is energy in, W electric in. And then you have energy out from the outlet. So you have this energy out is equal to MEHE, the mass of the exit mass, which we do have it now, HE, the enthalpy of the air which is leaving, and the enthalpy was also found up here. So we know it, and this is equal to delta U, and delta U is M2U2 minus M1U1. Kinetic potential energy is negligible. So M2 is known, M1 is known, we just found them down here, and U2 and U1 are also known from the air table up here. So if we plug in, therefore we can find the unknown in this equation is the electric energy. We can find the unknown in this process, electric energy. So the second part of the problem is to find the entropy generation resistance during this process. Okay, so again we start with the same generic or general equation, S in minus S out plus S generation is equal to delta S of the system. For steady flow processes, this delta S is 0. In this case, this is not 0. So entropy in minus entropy out. So is there any entropy coming in? There is no heat, there is no inlet, but there is work coming in, but that work coming in doesn't bring in entropy. Entropy associated with work is 0. So entropy in is 0. How about entropy out? We do have an outlet, so entropy out is simply MESE. Entropy MESE. Okay. Plus entropy generation, which usually we cannot do anything about it. It has to be found by finding the other terms, and it's equal to delta S of the tank. So delta S of the tank is equal to M2S2 minus M1S1. So delta S of the tank is M2S2 minus M1S1. So entropy generation is therefore rearranged as equal to MESE plus M2S2 minus M1S1. All of these terms have been found before in the previous slide. S1, S2, or no, we have found no. We did not find the entropies. Instead, so what we have found already is ME and M2 and M1. So in order to find the entropy difference, we go ahead and use the constant average. We go ahead and use the entropy relations based on constant Cp and Cv. So we also have the opportunity to go and use the air table. So if you go to the air table, you would need to use S0, so which is the most accurate. Here is based on the approximate equation for the entropy change of a gas. So now here the temperature of the exit gas is constant. However, the pressure is changing from 200 kilopascal to 500 kilopascal. So the average temperature is the average pressure is therefore 350. So if you go ahead and rearrange these terms here, let's see what we have. So here we do have, instead of ME, we can write it as M1 minus M2. And then this is M2S2 minus M1S1. If we rearrange them in terms of M2 and M1, then we see that M2 times S2 minus S exit and M1 S1 minus S exit. So this is like the condition of the air changing from 1 to condition of the exit air, and S2 between a state 2 and between a state of the gas during the exit process. So we know that S2 minus SE can be expressed as, for instance, based on the ratio of temperatures and pressures, Cp natural log of T2 over Te. Temperature doesn't change, so this term is 0. And then minus R log of P2 over Pe. Or this is for like between a state 2 and 1, or between a state 2 and exit. Between any two different states, this equation applies. So therefore it's equal to the natural log of P2 over Pe. And for Pe, we just use an average value because this is a uniform flow process. This is an approximation, but it's fine. Okay, so if we plug in the numbers, we find S2 minus SE, and similarly for SE minus SE, S1 minus SE, the same process, temperature 0, the ratio of the pressures, and we find the entropy change between these two states, 1 and E and 2 and E. So if now we go back to this equation and multiply them by their corresponding mass, here M2 S2 minus SE and M1 S1 minus SE, then we find entropy generation, kilojoules per Kelvin, and again it's positive. So the entropy generation is always positive. If you find entropy generation negative in a question, so something you have made a mistake somewhere. All right, so this brings us to the end of this lecture and to the end of this chapter. And feel free to send me questions by email and by course forum. Most of the questions that you may have, they have been addressed in the lectures, and particularly in the problems that we solve. We covered a range of problems from very practical turbine compressor pumps using the isentropic efficiency, and then closed system, steady flow, uniform flow in this last one, ideal gas law, steam refrigerant. Pretty much everything was covered during this solved problems. So whatever answer you may have, it's actually have been addressed. So okay, so thank you very much, and hope you will do well in the exams.